Okay, so our next speaker of the day is Mohammad Riajul Haq. He's from basically our home institute, Indian Statistical Institute in Kolkata, which is one of the host institutions, and we are very happy to have him. He's going to talk about decoding the physics of the early universe through primordial black holes, dark matter, and gravitational wave. So I will send you a reminder when 5 minutes are left.
Okay, Anish, thank you for the introduction. And also inviting me for this talk. So I will talk about the decoding the physics of the early universe through primordial black hole abundance, dark matter, and gravitational wave. So this talk will be based on these 5 references, and this work has been done is in collaboration with Subhashish. He's a final year PhD student at IIT Madras. Donald is a postdoc at IIT Madrid. Nilanjan is a postdoctoral fellow at ICT-PAP. Ian is my collaborator. He's is a professor at IJC Lab, University of Paris-Saclay. Siram Kumar is my former postdoctoral guide. And Debo Prasad Maiti is my PhD supervisor. So let's start. So in my talk, I initially try to motivate that what are the observational difficulties in the early universe and why we need this reheating phase. Because in my talk, my specific goal is to decode this phase of reheating. And then I move my discussion towards the standard dynamics of reheating, that why this reheating dynamics is needed. I'll give a brief introduction for the perturbative reheating scenario. Then I move my discussion towards the scenario where the primordial black holes are responsible for the reheating. So if one assumes that the primordial black holes is there in the early universe and formed after the end of the inflation during this reheating or the radiation dominated era, then is it possible to produce all the standard model particles from the evaporating black holes or not? So those possibilities I will talk about. And then I compare the scenarios, 2 different scenarios, because in case of PPH reheating, we generally consider either the monochromatic mass distribution or the extended one. So I will compare this monochromatic with the extended mass distribution and check how this our result is sensitive with this mass distribution. And then I will talk about the particle production from a single black hole, because the massive particle can also produce from the evaporating black holes. And we can estimate the entire dark matter parameter space from those black holes, the ultralight black holes. So once I have the ultralight, I discovered the whatever the parameter space for the dark matter and the reheating scenarios. Then I move towards the phase of the in terms of detection possibilities of this early universe through primary gravitational wave. And when I say the primary gravitational, that means this is only the tensor perturbation without any source term. So those tensor perturbations are generated due to vacuum fluctuation during inflation. And if it just evolves through epoch by epoch, and finally we calculate it today. So how this primary one, the primary gravitational wave, we can set light of the early universe. And then I move to a specific PBH formation mechanism. So if you have one specific formation mechanism, primordial black hole formation mechanism, like you have USR kind of model that leads to enhancement in the scalar small spectrum, and that leads to a generation of the primordial black hole. In that case, there may be a scalar induced secondary gravitational waves. And from this scalar induced secondary gravitational, I will talk about how it is compatible with the nanograph years data, and how we can constrain the reheating phase through these induced gravitational waves. And then I move to my final the part that how if you have a quantum correction in the Hawking evaporation, and that leads to a new mass window for the ultralight black holes, and how you can satisfy the dark matter parameter space. And I will also talk about just make some comments about the high frequency gravitational wave can restrict this kind of scenario. And finally, conclude my talk. Okay. Sorry, there's a problem. Oh. So what are the observational challenges in probing the early universe? So our knowledge about the cosmic history of the universe is based on the two measures observation. One is the cosmic microwave background, and on the other hand, there is Big Bang lithosynthesis. The cosmic microwave background provides an evidence of an early accelerated phase, which typically we call the inflationary era, and the energy scale of this inflationary phase is of the order of 10 to the power 15 to 10 to the power 16 GeV. If we talk about the large scale scenario. And the duration of this inflationary era is around 10 to the power minus 36 seconds. On the other hand, we talk about the Big Bang nucleosynthesis, which predicts the quantities such as the light element abundance. The energy scale is of the order of 1 MeV, and the time scale is around 1 second. So you can see there is a massive gap in terms of energy and the time scale between these two, the end of the inflation and the BBN. So, and here actually we need a radiation dominated universe in order to nucleosynthesis process, in order to start the nucleosynthesis process. So how this we can get rid of from the inflaton, that is the process of reheating. So, and another important aspect is that this reheating phase is very poorly understood from both theory and observational point of view, because there is no such observation. Whatever we have, some indirect imprints of. So what happens? So after the end of the inflation, the inflaton field goes down to the minimum of the potential, so it oscillates around the minimum. And if the amplitude of the oscillations is quite high, then there is some resonance kind of production can happen, depending on the coupling between the inflaton and the daughter matter fields. And in that case, we cannot use the perturbative expansion in the coupling parameter. So at the initial stage, there is some parametric resonance kind of phases there. And then when the amplitude of the oscillation is quite low, then we can treat the dynamics, the perturbative. So what happens? So after the end of the inflation, during reheating, all the entropy are generated. So the empty space is filled with the matter. So all the entropy are generated during the end of the reheating era. And one of the standard assumption is that after end of the reheating, the co-moving entropy density that should be conserved till the present day. So whatever the matter or the standard model dark matter, all are going to be produced during this time. So if you have this reheating scenario, then it basically modifies the expansion history. So it just took a particular scale, the CMB's pivot scale, and if you focus on the exit and the re-entry point, if you connect the exit point and the re-entry point epoch by epoch, then what happens? The duration of the inflation is get modified due to this due to this extra reheating. So in a particular inflationary model, the prediction for a particular inflationary model that get modified due to this epoch of reheating. So depending on your equation of state, the background equation of state, and the duration, for a particular models of inflation, the prediction for a particular model of inflation will get modified. So the prediction for the tensor to scalar ratio or the spectral index, the scalar spectral index, that will get modified. So that has a dependency on this reheating phase. So now if we just move towards what is the background dynamics during this reheating. If we ignore this non-perturbative era, this parametric resonance, and once we consider once we in a weak coupling regime, so where the non-perturbative production is subdominant, in that case, we can fit this analysis perturbatively. And another issue with this parametric resonance production is that that for phi square kind of model, we cannot get rid of from the entire inflator at the end of this non-perturbative era. So at the end, we need some perturbative scenario in order to decay the entire inflaton into the standard model particles. So in order to deal with this energy density associated with the inflaton and the standard model particles, we have to calculate the collision term. And this collision term is dependent on what is the kind of interaction we are taking between the inflaton and the standard model particles. So there are two terms associated with it. One is the redshift part that will depend on the background equation of state, which is governed by the inflaton, and this is a decay term. So the evolution of this rho phi is basically depends on a to the power minus 3 into 1 plus w, and there is associated e to the power minus exponential decay term. So once your decay term is dominant over your expansion, then the inflaton width decays very fast, and we get a radiation dominated universe. And another thing we need to calculate here, that is the average inflaton equation. How we calculate? if you have assumed the potential is behaving 5 to the power 2n at the minimum, and if you take a single oscillation, and if you the average of these oscillations, then you can connect the phi dot square, the kinetic energy, with the derivative of the potential. And finally, we'll achieve that the rho W phi is basically the n minus 1 by n plus 1 for phi to the power 2n kind of potential. So once you have the inflaton equation of state, and if you work this Boltzmann's equation, so finally there is a crossover between inflaton and the radiation energy density, and you will get a radiation dominated universe. And these are the possible reheating scenarios generally considered in the perturbative preheating dynamics. If it's some possible take a possible interaction between inflaton and the radiations. So inflaton can decay in the scalar, it can decay into the pair of fermion, and there may be some gravitational production can possible. So these are the different decay width associated with the different interaction channel. So now I'll specifically focus a particular scenario where the primordial black hole is there. So if one assume the primordial black hole is present after the produced during this reheating era or during this standard radiation termination, then what? So what are the possibilities of this PBH formation? So the standard scenario is the most explored scenario is the if people are generally taking ultra-solar kind of phase during inflation. So it typically say there is a speed breaker term in the potential or in the inflection point in the potential that basically slows down the inflaton. And the power spectrum is proportional to the 1 over 5 dot. So there should be an enhancement in the scalar power spectrum. And when this overdense region re-entry during preheating or the standard radiation domination, depending on how much dense it is, if it's greater than some density contrast, then it can collapse and form PBHs. On the other hand, during this preheating era, the instability, the inflaton instability can also lead to a formation of black holes. So during this preheating stage, when the inflaton are oscillates, so in that time, in that duration, the density perturbation that can be amplified, and in that scenario, if the amplification is quite large enough, that should can responsible for the structure formation. And as a possible scenario, primordial black holes might form. And there are subtle condition is present there that what should be the collapse time and the duration of the non-perturbative the resonance era, non-perturbative era. Depending on that, the primordial black hole can form. And there are other possibilities like bubble collision during phase transition and in principle that can also happen. So these are the possibilities. But in my talk, I will not emphasize what are the formation mechanism associated with the primordial black hole. Rather, in the initial part of my talk, I'll interested that if the primordial black hole is there, and we are interested to production of the standard model particles and dark matter from this, then what will happen? So the revolution of the primordial black hole, it depends on the three parameters. So one is the mass distribution. So what kind of mass distribution we are taking, that is depend on the what kind of formation mechanism is associated with the primordial black holes. But in a fast node, we typically choose a monochromatic one. So to a fixed mass, and the formation mass can be connected with the horizon size at the point of formation with some collapse efficiency. So you can treat collapse efficiency, you can connect it with the background equation of state, or you can treat as a free parameter. And on the other hand, we have the beta. So how much energy falls into the black hole at the point of formation. So that is beta is basically the beta formation, rather we can say it, beta formation. That is the PBH energy density over the total background energy. So once we have all of these things, we have to evolve the primordial black holes energy density from formation point to the evaporation point. And after to do that, we need the energy spectrum of the emitting particle. Because as I say, the walls are ultralight in nature, and the Hawking due to the Hawking evaporation, all the fundamental particle can produce. And here I have plotted, I have shown here the spectrum of the different spinning particles. This is the number of particles emitted per time per energy scale. And that is related with the gravity factor. So what is the gravity factor? Gravity factor is the transmission coefficient, the wave from horizon to infinity. So that is related. So this flux is related with this gravity factor. And here we have in the right plot, I've shown that how the absorption cross section varies with the energy scale, the energy of the emitting particle, and have shown for different spinning particle. And ultimately, we only have the analytical estimation in the high frequency limit. So, once we have the flask, now if we integrate out over the entire energy scale from 0 to infinity, we'll get the exact evaporation function for a particular species. Now, if we're interested only in the production of the standard model particles from evaporating primordial black holes, then we need to sum over all the standard model degrees of freedom. And here I've shown that how the evaporation function is varies with the mass of the emitting particle. And there is some geometrical optics limit, as I already mentioned, that there is some analytical estimation in the high frequency limit. And we have the exact numerical behavior from the black hole. So if we just compare this, we can see that for the spin zero particle, this green one and the geometrical optics limit are almost matches. But for the higher spin particle, there is a deviation, and there we need the exact numerical analysis. So then we need to calculate everything from the energy spectrum, whatever we are getting from the black hole. So what are the restrictions in the pH parameter? So here we are interested in only in the ultralight black holes. Those are evaporated before BBN, because otherwise, if the black holes are evaporated after BBN, so there may be some restriction from the delta negative perspective, and pH can dominate, so it can hamper everything. So that's why we are interested in the evaporation of those black holes before BBN. So that will restrict the black hole mass below 10 to the power 8 gram. And another restriction is the what is would be the minimum value of the primordial black hole. So that if we consider in the collapse mechanism, so the collapse of the horizon size at the end of the inflation typically gives you the minimum mass, and that is around 1 gram. But technically, we can go to the Planck scale, which is around 10 to the power minus 5, I think. So, but in this work, we basically focus on this mass level, 1 to 10 to the power 8 to 10 to the power 9 gram. So once you have the range for the ultraviolet black holes, then there are some restriction on the beta, because those black holes can dominate. And in that case, there are some density fluctuations present due to the inhomogeneities in the pH distribution. And that can and that can lead to isocarbonation perturbation. And during this pH domination, those isocarbonation perturbation convert into the adiabatic one. And the tensor perturbation at the second order can be sourced by this, and that will lead to secondary gravitational wave. And in that case, from delta and effective bound, there are some restriction on the beta. So once we have those restrictions, by considering this, if we go to the how the black hole energy density evolves during this reheating era from the formation point to the evaporation one, this is the decay term. And in order to calculate this decay term, we assume that the moving black hole number density, primordial black hole number density, is conserved. And the radiation energy density is now sourced by the two different sources. One is from the inflaton, and the another one is the primordial black hole. So there is a competition between the decay of the inflaton and as well as the evaporation, black hole evaporation. So, and the lifetime is fixed for a once we have the particular mass of the black hole. So then we evolve the inflaton radiation and as well as black hole energy density, and see what are the possibilities we have depending on the different black hole parameters. So these are the evolution of the energy densities in the left plot, where we have the without primordial black hole. So we took a particular coupling between inflaton and the standard model particles. We took a epoch kind of interaction between inflaton and fermion. And so if the coupling value is 10 to the power minus 4, so then just follow the solid lines. The blue one is the inflaton and the red one is the radiation. So there is a crossover. So we are getting a temperature around 10 to the power 7 G. On the other hand, if you have a black hole, then it can dominate and get much higher temperature. So this is the pH dominated scenario, where the standard model particle is produced due to the evaporating from the evaporating black holes. But in the other case, there may be possible the primordial black hole is not dominating, Even it evaporates in an inflaton-dominated background like this, in that case also, we can achieve radiation-dominated universe from the PBH evaporation. But point to be noted, then we need the inflaton equation of state is greater than 1/3. So we need that the inflaton redshift large, much greater than the radiation, much higher than the radiation. Then only we will achieve such kind of rating. And another point to be noted, that there is a relation between this critical value of the beta with the coupling between inflaton and daughter field. So if your beta value is greater than that, then only you will get this PBH reading scenario. And the right hand side is depend and whatever the coupling present between the inflaton and the standard model particle. So depending on the strength of the coupling, and if the inflaton equation of state is greater than 1/3, then it is possible that even the black hole evaporated in inflaton-dominated background, but still will manage to get a radiation-dominated universe from PBH evaporation. So in that case, the reheating temperature is depend on two parameters. One is the beta and also the formation mass of the black hole. But in the other scenario, what happens if your beta value is large enough, the PBH itself dominates, like just for the green one, so it dominates and then it evaporates and leads to a radiation domination. In that scenario, your reheating temperature is not a function of beta because already your universe achieve a PBH dominated universe. Beta goes to 1 before it evaporates. So it's independent of the formation beta. It only depends on the formation mass of the primordial black hole. So once you have this, that is the point. Even for PBH, without PBH domination, it is possible to get a radiation-dominated universe from PBH evaporation. Then let's compare the monochromatic mass distribution with the extended one. In the extended case, what happened? We need the mass distribution function. This is the number density of the black hole over a mass range m to m plus del m. And if we integrate over the mass range, then we get a black hole number density. So in the Boltzmann's equation, now here also have a mass integration, depending on the what kind of mass distribution we are taking. And if you compare the mass distribution with the extended and the monochromatic one, so if your extended mass distribution has some peak, and if you take the monochromatic one with the same peak value, then the result will be almost same for both the monochromatic and the extended one. But it's possible, like the violet one, that is extended to 10 to the power 1 to 10 to the power 6. In that case, we'll have a different result from the monochromatic analysis. But if we have some peak values, so naturally that will lead to the monochromatic result. So how does PBH reheating scenario behaves here? I've shown here in the right plot. Just follow the right plot, black curve. It is for the inflaton standard model coupling at 10 to the power minus 5. So initially it is beta independent. So this portion is dominated by the inflaton. So inflaton governs the reheating dynamics. Then after some point, we can see that there is a beta dependency is available. So your reheating temperature, the starting point of radiation domination, that's the reheating temperature. So it depends on the beta value. And then there again for higher beta, this is beta independent. So this is basically the PBH domination. So there is PBH independent, independent of beta during some inflaton dominated case. When inflaton is dominate the production of the standard model particle, then there is a PBH reading scenario, and after that again the PBH reading with PBH domination, where this is beta independent. Now we move to the production of the massive particle from this evaporation. So this is the number of particle emitted per unit time, per unit energy scale from a Schwarzschild black hole. And if we just integrate over it over time, from T into T evaporation, from formation time to evaporation, then we finally calculate the number of particle emitted per black hole. And if you're, but note that if your mass of the emitted particle is less than the black hole formation temperature, then only we can integrate from formation to evaporation. Otherwise, if your mass of the emitting particle is greater than the black hole temperature, then initially it is kinematically forbidden. But when the black hole evaporates, your black hole temperature got increased. Then we can, after some point, when mass of the emitting particle is equal to the black hole temperature. From that point, those masses are produced. So integration should be from TJ to T evaporation. So once you have the number of particles emitted from a single black hole, then you multiply it with the black hole number density, you get the dark matter number. The yield, the number density of the dark matter over the entropy density, that is conserved from reheating point to the present day. So if the evaporation point and reheating point are different, so then we need to evolve it up to the reheating point, and then finally we can connect it with the present day and calculate the dark matter very carefully. So these are the results for the PBH domination case. And if we move the scenario where PBH is not dominating, and we have several values of Wi-Fi. Wi-Fi 0 means this is also PBH reheating without domination. And if we increase the coupling parameter, that means we are inject more entropy in the system. And in that case, we need more higher mass of the black hole to satisfy the correct value. The higher value of the dark matter mass to satisfy the correct value. And here I have quoted the different dependency for different situations, like mj less than formation black hole formation temperature, for inflaton reading, for PBH reading scenario, because in standard model particle is produced from both inflaton and the black holes, and whereas the dark matter is produced solely from the PBH evaporation. So now move to the situation where I'm interested to decode this phase. So in order to decode the early universe, initial interest in the primary gravitational. As I already mentioned, the primary gravitational means the tensor perturbation are produced due to the vacuum fluctuation during inflation. We have no source term there, and we just evolve it epoch by epoch and finally calculate to the present day. An important point is that the gravitational energy density is simply decreased as a to the power minus 4, redshifts as a to the power minus 4. Whereas our background during the reheating is redshift as a to the power minus 3 into 1 plus W, depending on the W. Like in kination, is a to the power minus 6. So there is a relative redshift present there. That's why we're getting a slope in the GW spectrum. So there is a tilt, and we'll get a blue tilted spectrum for W greater than 1/3, and we get a red tilted spectrum for W less than 1/3. So if I have a W greater than 1/3 scenario, so there is a possibility to probe it through the future gravitational emissions like LISA, ET, DCO, or BBO. So in the next slide, I'll show that how LISA, ET, DCO, BBO, the future gravitational emission, can shed light on the early universe physics, like in the fundamental couplings between inflaton and the standard model particles. Like these regions are the consistent region with the observation. And to achieve this result, we use the SNR formalism. So we have the GW spectrum for the primary one, and we have the noise curve associated with it. If we just indicate out from these frequency ranges for those gravitational emission for a observation time like 4 years to 5 years, then finally we'll get a SNR, signal to noise ratio. And if it is greater than some threshold values like 10 to 5, then it can be measured. So we typically choose these threshold value for the observations. So these are the different reheating scenarios, and those these fielded region are indicate that those are compatible with those gravitational emissions. And this is the PBH rating scenario we have also mentioned. Now move to the next scenario where we are interested in the stable black hole, the higher mass black hole. If the black hole mass is primordial black hole mass is above 10 to the power 15 gram, so those black holes can act as stable, and that can be treated as dark matter. So there, if we can consider a formation mechanism associated with this primordial black hole, like use a kind of model. So in that case, there are some interesting scenario will arise from the particularity of gravitational wave, because there is a scalar induced gravitational can produce in that case. So what are the formation mechanism? As I already mentioned, that I am interested in the scale, this green one, lambda PBH, which is much smaller than the CMB. And this is the schematic presentation of the PBH formation. So if you have inflection point or in the speed breaker term in the inflation potential, which leads to enhancement in the scalar plot spectrum, that can lead to PBH formation. So in that case, what happened? Because in the linear order, the tensor perturbation, scalar perturbation, all are independently. But in the second order, the scalar perturbation at first order can be sourced, the tensor perturbation at the second order. And that leads to a secondary gravitational wave, the scalar induced gravitational wave. But for the scale invariant scalar power spectrum, there will not any difference, because that is always subdominant. We'll get an amplitude about 10 to the power minus 22. But if you have an enhancement in the scalar power spectrum, that leads to a enhancement into the gravitational spectrum and make it compatible with the nanograph observations. But one of the issue with such kind of gravitational wave, the scalar induced gravitational wave, is that it overproduces dark matter. So to make consistent with this observation in the background, we also calculate the FPBH. So what is the FPBH? That is the fraction of dark matter that contributed into the primordial black hole. So FPBH 1 means 100% of dark matter at the present day that can consist of the primordial black hole, the stable primordial black hole. And now, what are the scales we are interested in? So we are interested in the small scales. So your scale light to be 10 to the 8 to 10 to the power 16 to 17 meter per second inverse. And in order to get primordial black holes, the amplitude should be much large, above 10 to the power minus 3 to 10 to the power, about 10 to the minus 3 to, or 10 to the minus 2, close to 1. So once we have the primordial black hole, so and we are interested in the scalar induced gravitational wave, and where we assume that the scalar power spectrum has a broken power law kind of behavior. So there is a scale invariant part, and there is a enhancement part, and the ascending part we choose as a k to the power 4, because most of the USR kind of model is BF like this. This increment in the k to the power 4 kind of enhancement depend. But the descending part we choose as a free parameter, and finally we'll fix it through the observations, the nanograph observation. Okay. And to calculate the dark matter abundance and the PBH formation, we consider analytical expression for the density contrast depending on the background equation of state. And we're also interested in that this is not exact, so there may be some error bar will be associated with it. That's why we vary it from 0.5 delta C analytical to 1.5 delta C analytical to see what are the difference we'll get in the final result. So once we have the spectrum, then we're interested to arrive the base fit values in compressing with the nanograph frequency data. And to do that, we use PTRK in careful mode. And if we have 4 different models. In the R4PF, we have 4 free parameters. One is K peak, the amplitude of the scalar power spectrum A0, WRE, the background equation of state, and the descending part of the power spectrum N0. And we choose a wide range of power values. And here we can see that, in our result, we see that our analysis is not sensitive with the N0 values. So that's why in the R3PF run, we fix it with the base fit values, or you can fix it -2 or -1.5. That doesn't matter. The result is not much sensitive with the N0 value. But the problem with these free runs is that we did not consider any constant from the FPBH. That's why in the bound run, we take constant from the FPBH. So we connect the Kp, K0 and Kp and A0 with the mass of the black hole and the FPBH. And we vary FPBH from 10 to the power minus 20 to 1. And let's see that what will be the expected values for 3 different set of critical density contrast. As I already mentioned, that we vary critical delta C analytical from 0.5 delta C analytical to 1.5 delta C analytical to see how much is sensitive with the density contrast. And finally, we took the R2PB run in the bound run. In the final bound run, what I've considered that FPBH, okay, fine. So we already know what are the constant available on the FPBH, depending on the lensing and the gamma ray observation. We put the restriction there, and we did not make it free. And then we run this M and WR. So in the all cases, we see that for delta C analytical, our result lies the background equation of state is around 0.6, around 0.6. Whereas for 1.5, it is closer to radiation, and for 0.5 delta C analytical, it's closer to the kination domination. It predicts basically the kination reading. Now, here plotted the marginalized posterior distribution of the parameters on that arrive in comparison with the nanograph 15 set data for both the bound runs. And there you can see for delta C analytical 0.5 delta C analytical, the yellow one, and just follow the blue one. The yellow one, you can see that the highly marginally satisfied, because here the FP is close to 1. Only the FP value is very close to 1, and it's marginally consistent with the nanograph 15 set data. Even that is also clear from this. If we just plot our base fit value on the sensitivity, or nanograph sensitivity, the violent kind of plot, there we see that the 0.5 delta C article is not fitted well. The base fitted values for 0.5 delta C article is not fitted well. And for the base fitted value, if we calculate the FPPH, then we can see that the problem is there for the free runs where we did not consider any constant from the FPPH that has a dark matter overproduction. But for bound runs, it is consistent with the bound. So once we have this, then finally we do the base factor. And in order to do that, we calculate the marginalized likelihood in support of our model, and we choose R2PB model, the final one, where we have the FPBH restriction in there, and utilize it to evaluate the Bayesian factor against our reference model is supermassive black hole binaries. And we get a strong Bayesian evidence for if for density contrast value is 1.5 in analytical, and even for analytical 1 also. But for 0.5 density analytical, it is that it is almost same. We get a order 1 value of the Bayes factor. Okay, so till now, I have discussed that how the ultralight black holes are responsible for the production of the standard model particles, dark matter, and how we can decode the early universe physics through primary gravitational wave. And another gravitational wave I have explored that which is related with the PBH formation. And then another interesting scenario I want to just mention at last, that possible that recently the devalued, I think last 3-4 years, devalued wrote several papers related to that how the quantum correction in the PBH Hawking evaporation leads to the other possibilities, like the small black hole can be stable, still present, and keep rise a new mass window like this. So what happened actually, because all our standard Hawking evaporation calculation is based on the semi-classical approximation. And in that case, what happened after, at least after half-life or after certain fraction of the evaporation process, we can.
Riaj, 5 minutes left.
Okay. So we need to take into account the back reaction effect. So that leads to a reduction into the evaporation process. And that can be parameterized through the entropy that consists of the black holes. And the power, this K basically is, you can say as a memory burden strength, and Q is the parameter that indicates that after which fraction this memory burden effect will start. And just follow the left plot. These are all parameter space for the ultralight black hole. So initially, when I talk about in my first few slides, the ultralight black holes, I considered from 1 gram to 10⁹ gram, and all are evaporating them. But now, depending on this quantum correction in the evaporation process, it may be possible that some portion of black hole are stable, depending on how much correction we are taking. So these are the region for the stable black holes. Those are evaporated by 2 days, and there are some restriction from the extragalactic gamma rays and CMB isotopes. And this is a new mass window that opened here. But I don't think this mass window will be correct, because recently we are observing that if we take the high frequency gravitational wave into analysis, maybe there's some restriction on the FPBH here. So now finally we calculate the dark matter parameter space in this scenario. And just I want to mention one important point. If we just parameterize Q as a free parameter, and like we consider that 99% of the black hole are evaporated due to Hawking evaporation, then becomes stable. So then it's possible that at the final release, there may be a contribution from the evaporating black hole. So we cannot take FPV equals to 1 only from the stable one. So here in some parameter region, depending on the mass of the emitting dark matter, there is a competition between the stable one and the evaporating the dark matter which is produced due to the black hole evaporation. Because the initial part is dominated by the Hawking evaporation, then there is the memory burden part which make it stable. Okay, so I finally conclude my talk. So initially start with the brief overview of this background dynamics of reading, basically the perturbative reading scenario. Then I discuss the how. If you assume the primordial black hole is there, then depending on the beta parameter or the mass of the black hole and the coupling between inflaton and the standard model particles, there may be two possibilities. In one case, the black hole can itself dominate, and then the evaporation leads to the production of the standard model particles. In the other case, what happened? That black hole is not dominating, it's evaporated in front of the background. Still, we are getting all the standard model particles from the evaporation. And finally, we consider the dark matter parameter space, calculate dark matter parameter space solely from the PVG operation. Yes, you can say that there are other sources can be there from the inflaton dark matter can produce or from the thermal bath also that we have not considered. And then I try to decode this phase of early universe through primary one. Then we consider the certain formation mechanism, if certain formation mechanism associated with this primordial black hole, and that leads to a secondary induced gravitational wave. How the secondary induced gravitational wave can shed light on the early universe physics from using through the PTA data. And finally, I consider the memory pattern effect and show how the new mouse window will open and that give rise to new possibilities for the alternative approach. Okay, thank you.
Okay, thank you for the nice talk. Any question from the audience? Please unmute yourself and ask.
Hello, may I ask a question?
Yes, please.
Yes.
Hi, Raju.
Hey, hi, Samadhan.
Yeah, nice talk. Yeah, just one or two questions maybe. So for primordial black hole, what about the horizon distance?
What about the horizon distance?
Because you are consequently saying the black hole, black hole, black hole. So what about the horizon? Because
no, actually, typically the black hole mass is whatever I consider is comparable with the horizon size. So entire horizon is collapsing. The fraction, you
so
can say. There is some gamma parameter will be there, but there is a fraction, but that calculation is, I think, difficult one. So typically it is the horizon size with some factor.
With some factor. Okay. So can you go to slide number 11 or 10 where you show the emitting part, the rate of emitting particles? QS or something like that. No, then 10. Slide number 10. Yeah, this one. So this QS is the rate of the emitting particles, right? Which is like the Planck spectrum.
Yeah, it is like a spectrum, the flux of the emitting particles.
The flux of the emitting, that is the Hawking radiation, like.
Yes.
Okay. Then my question is, your primordial black hole is the dynamical, right? It is not static. It is dynamical in nature. Then under this dynamical scenario, are you sure the emitting particles still follow the Planck spectrum? Because what we do is the static black hole case. In the static black hole, we know that the emitting particles follow the Planck spectrum. But are you sure is it still true for the dynamical black hole case?
No, but ultimately, so I'm calculating from the gravity factor that is related with the absorption cross section.
No, but you are writing a Planck spectrum like spectrum.
No, that spectrum is I've taken just coming from the Black Hawk code. They all taken this kind of thing. From the static black hole, what kind of spectrum you will get, or from the car one, if it's a rotating one, then they have calculated for the spectrum of the emitting particle.
Okay, so it is still true for the dynamical scenario.
It's true for the things. It is true for the, I think, the time you consider, because it is only depend on the your black hole radius, I think, and the energy of the emitting particle.
Okay. Okay. Thank you. Thank you.
Yeah, if I may make a comment here, so strictly speaking, this is absolutely not true, because in the
Exactly.
in the spectrum, when we calculate, so when we say it's a thermal distribution, which is a Planck distribution, right? This is just a black
Exactly.
body distribution. This is assuming that the black hole is static. However,
Exactly. And we also assume an equilibrium thermodynamics.
Yeah. So,
Yeah.
but the main point in Riaj's analysis, if I understand correctly, is the fact, and also this is taken into account in the black hole codes and all this codes, is the fact that the universe expands, right? That there is an expansion of the universe, and these are very ultralight primordial black hole presence in the post-inflation. So, in those scenarios, black hole is obviously not it's not the solution of your entire geometry, right? It's just some object which is present in a very large expanding universe, right? So in those cases,
Okay.
this is okay to assume such a distribution.
Okay. So it's just an
so in
assumption. It's an
principle,
assumption.
yes. I think so.
Okay. Thank you.
In
Thank you, Riaj.
any other question from the audience, please unmute yourself and ask. Okay, if not, let's thank the speaker once again. Thank you for the nice talk. And will you be able to